Cool. We have been talking about detecting deadlocks once they happen, and the previous case we discussed was when you have only one instance of each resource type. So there it's very simple, right? You can either straight up take your resource allocation graph and look for cycle, or if you want to simplify things a bit, you convert it to the wait for graph and then again run a check for cycles, and you know there's a cycle, there's a deadlock. If there's no cycle, there's no deadlock. It's as simple as that. But when we have multiple instances of the same resource type, you will remember from our discussion on resource allocation graphs that just because there is a cycle, you cannot say there is a deadlock. So for example, you might have 3 printers, so the resource type is printer and you have 3 instances, so there might be a cycle in your resource allocation graph, but because you have multiple instances, it might not necessarily translate into a deadlock situation. So I spoke about this point in a little more depth. I believe I also illustrated with an example when I was talking about resource allocation graphs and how to detect a cycle using them. So if you need any clarity, I would encourage you to check out that segment before proceeding. Right, so this is the case where we ended with ambiguity, right? The RAG could not really give us valuable information in this case when you have multiple instances of the same type as to whether there is a deadlock or is there not. So now that dilemma will be solved in this segment. We have a formal algorithm which is going to help us determine whether you have a deadlock or not. So I will first quickly walk through the algorithm. These screenshots, by the way, are from the Silberschatz textbook. So I'll quickly walk through the algorithm, then we will take an example from the same textbook and work it out, and after we work out the example, I will tell you what the algorithm is asking you to do and why, what exactly are we doing or what is the meaning of it. So I think once I give you the example and explanation, things will be clearer hopefully. So if after just looking at the algorithm you're not quite able to make sense of things, just hold on with me for till the end of the segment. Right, so we'll first look at the algorithm. So what are the things we are initializing? So we're first initializing an array called available, a vector or an array of length m indicating the number of available resources of each type. So let's say you have 3 types of resources, for example processors, printers and something else, say monitors or whatever. So you have 3 resource types, and of each type you have a specific number of instances. Let's say 3 printers, 2 processors, 5 monitors. Then your available is going to be 3 to 5. That's the array, right? Okay, next, allocation is an n cross m matrix that defines the number of resources of each type currently allocated to each thread. So m, as we already saw, is the number of resource types. So n is the number of threads or processes we're dealing with. Again, I will illustrate all of this with examples, so stay with me. So allocation is an n cross m matrix which talks about how many instances of each resource type has each process taken up. So process P0 has taken up 1 printer, 1 monitor and no processors. P1 has taken up 2 printers, no monitors and 1 processor, and so on and so forth, like that. That is allocation. Allocation refers to how many have been currently allocated. Next is request. So request again is an n cross m matrix which indicates how many each process is now asking for. See, so some resources are already there with the processes, with the threads. Thread and process will be used interchangeably in this context. Some resources they are asking for. So that's the whole template we've been seeing, right? So even when we were discussing the necessary conditions for deadlock, there was this analogy I was repeatedly using about, you know, taking up an exam, and in that context I said I have my stationery but I do not have my calculator and I'm now trying to claim the calculator. So that's the kind of scenario we'll be dealing with mostly. So you have some resources, you need some more resources, and those resources either they're available or they're taken up by someone else. That's the whole headache here. So allocation is about what you already have, request is about what you are asking for. Alright, so that is the data we are initializing. And what does our algorithm tell us? Let work and finish be vectors of length m and n respectively, where m is the number of resource types and n is the number of processes, right? So work is equal to available. So work is basically the same as available. It's just a copy we are creating because you don't want to make modifications to the original data. So basically work is going to denote how many instances of each resource type are available at the particular instance, right? So this process has finished executing. It gave back its resources to me. So now I have this many processes, this many monitors, this many printers. Now this process wanted these resources, I allocated this much to it. So now I have these many processors, monitors, printers. So that information will be stored in this array called work. So initially work is equal to available, right? Because this is your initial, how much is available is what you've stored in this vector. So that is what is going to be in this array also called work. And then as and when processes come and go, as and when they claim some resources, as and when they return some resources, we'll be updating the values in work. I'll show you how. Next, there's another called finish of length n. N is the number of processes. So finish is a Boolean array. So you initialize everything to false, and then as and when you complete a task, you will set finish equals true, right? So see here, if allocation is not equal to 0, then finish for that process is false, otherwise finish equals true. What are they talking about here? So what they're saying is, if you take any process I, Pi as in P0, P1, whatever, if the number of resources currently allocated is 0, then you set finish equals true, otherwise finish equals false. Why so? Because we assume every process has made a claim on at least some, if not all, the resources it needs. So some resources have been allocated to every process. Some others maybe it is waiting for, maybe it is not waiting for, but we assume allocation for any pending process is always non-zero. So if allocation is 0, it means the process has finished its work, so you set finish equals true. Otherwise, if some resources are in the possession of this process currently, then you set finish equals false, meaning it has not finished its job yet, right? So this is also some initialization. Now you find a process I such that finish is false, meaning it has not been finished yet, and request less than equal to work. So I will explain the meaning of these conditions shortly. As of now, just stay with me. So you have to find a process. You have all this data, right? Finish has been initialized, work has been initialized, request has been initialized, all this data has been initialized. So you simply need to look up the values and find any process such that both these conditions are satisfied. So if you find such a condition, you go to step 3, you do these changes. You set finish equals true, you go back to the work array and you increment it by the allocation of that process. Again, I'll give you examples, don't worry. So let us say process P0 is the one that satisfies these two conditions, then work is equal to work plus the allocation corresponding to P0, and then finish of 0 equals true. Again, you will keep repeating this until you are no longer able to find a process that satisfies both conditions. Now, once you reach that situation where I am no longer able to find this process, a process which satisfies both of this. So once this step 2, step 3 loop breaks, you check the finish array. So finish is a Boolean array, right? You check the values, finish of 0, finish of 1, finish of 2, so on. If all of them are true, it means everything has finished executing, well and good, your job is done. If some finish of I is false, but you are still not able to find some process that satisfies both these conditions, then the thread is deadlocked. Okay, so if things are not very clear, we're going to have an example and then there's going to be a more detailed interpretation as well. So please don't worry. I will quickly recap the algorithm, then we'll move to the example and things will get clear. Right, so what is the idea of this algorithm? You want to detect a deadlock when there are multiple instances of the same resource type. So you start by initializing some stuff. Available is an array of size m where m is the number of resource types. So for each resource type, how many instances do I have? X monitors, Y printers, K processors, blah blah blah. Allocation, n cross m matrix, where n is the number of threads or processes, m the number of resource types again. Each thread, how many instances of this resource type has been allocated. So P0 has X processors, Y monitors, Z printers. P1 has taken M processors, K printers, whatever, so on and so forth. Number of resources currently allocated. Request is again n cross m. Number of instances it is asking for, right? So that is some initialization. Further, we have work, which is again initially equal to available, just a copy of the same array. Finish is a boolean array. For any process whose allocation is non-zero, finish of I equals false. For any process whose allocation is 0, finish of I equals true. Now, with all that initialization done, you start with your processors I. I stands for the process index, so P0, P1, P2, so on and so forth. You find some process which satisfies both these conditions. You update according to these conditions. Repeat step 2, step 3, keep repeating until you are no longer able to find a process satisfying all this. Then go to step 4. So once you are no longer able to find a process that satisfies these conditions, check the finish array. If all the items in the array finish are true, it means all your processes have completed execution and there was no deadlock. If some false value exists at some index in the finish array, it means that your set of processes, there is a deadlock, right? So that was the algorithm. In the next segment, we'll go through an example and then we'll also see what exactly is happening here.